Question number 10. A cylinder having a diameter of 50 centimeters rolled down on an inclined surface from the height of 29.4 centimeters to the bottom of the inclination. If the cylinder at the top of the inclination starts from the rest position, what would be its linear and angular velocity at the bottom of the inclination? एक सिलेंडर है जिसका डायमीटर 50 सेंटीमीटर है। अगर ये सिलेंडर इंक्लाइंड सरफेस जिसकी हाइट 29.4 सेंटीमीटर्स है उसके टॉप से रेस्ट पोजीशन से स्टार्ट होकर बॉटम की तरफ रोल करके आए तो बॉटम पर इसकी लीनियर वेलोसिटी और एंगुलर वेलोसिटी कितनी होगी? We are given that there is no friction between the surface of the inclination and the surface of the cylinder, which means all the frictional forces are zero and losses due to friction are zero. The cylinder at the top is at rest. यहाँ पर इस सिलेंडर की टोटल एनर्जी इसकी पोटेंशियल एनर्जी है जो इसमें इस हाइट की वजह से स्टोर्ड है। अगर ये सिलेंडर यहाँ से रोल करके यहाँ बॉटम तक आएगा इसकी ये पोटेंशियल एनर्जी पूरी काइनेटिक एनर्जी में कन्वर्ट हो जाएगी। जैसे ही ये इस हाइट से नीचे आएगा ये अपनी पोटेंशियल एनर्जी लॉस करेगा और काइनेटिक एनर्जी गेन करेगा। ये काइनेटिक एनर्जी दो किस्म की होगी। एज दिस सिलेंडर इज़ रोलिंग डाउन, ये रोटेट भी कर रहा है और ये ट्रांसलेट भी कर रहा है। सो इट विल हैव rotational kinetic energy as well as the translational kinetic energy. The bottom line is यहाँ पर इसकी जो तमाम पोटेंशियल एनर्जी है वो बॉटम पर पूरी की पूरी काइनेटिक एनर्जी में कन्वर्ट हो जाएगी। इसके अलावा इसकी यहाँ पर जो पोटेंशियल एनर्जी है वो फ्रैक्शन के अगेंस्ट भी यूज़ होगी, बट एज वी आर गिवन that the fraction here is 0, so the fractional losses are also 0 joules. Hence we get that the total loss in potential energy will be equal to the gain in rotational kinetic energy and translational kinetic energy. Potential energy is given by mg h, where m is the mass of the body, g is the gravitational acceleration, and h is the height. Rotational kinetic energy is given by half I omega square, where I is the moment of inertia of the body, omega is the angular velocity of the body, and then the translational kinetic energy is given by half mv square. M is again the mass and v is the velocity of the body. Again mgh is equal to half into half mr squared. The moment of inertia of a cylinder is given by half mr squared. Omega, from the relation between the angular velocity and the linear velocity we have, omega is equal to v by r. So this value of omega is replaced here, plus 1 over 2 mv squared. Let's sort and simplify this long expression. As we know that m is common in all the terms, divide it everywhere and this m will be cancelled out. 1 over 2 times 1 over 2 gives us 1 over 4. The square is on both of them, v squared and r squared. R squared divided by r squared gives us 1. So this thing becomes this. GH is equal to 1 over 4 v squared plus 1 over 2 v squared. 1 over 4 v squared plus 1 over 2 v squared is equal to 3 over 4 v squared. Arranging this thing for v squared, we get v squared is equal to 4 by 3 gh. Taking square root on both sides, we get v is equal to 4 by 3 gh under the root. Plugging the values, we get 4 by 3 into 9.8 meters per second squared into 0.294 meters, that is the height of this inclination. Calculating this thing, we get v is equal to 1.9 meters per second. The linear velocity at the bottom of the inclination is 1.9 meters per second. Now, for angular velocity, omega is equal to v by r. V, as we have calculated here, is 1.96 meters per second, and the radius of the cylinder was given d by 2, 0.5 divided by 2 would give us 0.25 meters. Divide this term by this, we get omega is equal to 7.84 radians per second. So at the bottom of the inclination, the angular velocity of the cylinder will be 7.84 radians per second.